everyone, and welcome back to the Information Bottleneck. And today we have a great guest, Ion Stoica. So Ion, he's he's a professor at Berkeley, and he co-founded many companies, many startups, Databricks, right? Arena, LM Arena, and more. He's the guy that his lab invented vLLM, Ray, SGLang, and many other tools and software that all of us are using today. So, Ion, thank you for joining us.
Thanks for having me. Really appreciate it, and appreciate the nice introduction. The only caveat there I will say is that actually the students invented all of this stuff. So I think they should take the credit here. Yeah.
Okay, great. Yeah. So I think we can start with, I don't know, maybe the first question that I had in mind is how you actually you're doing it, right? Like how you're taking like so many research ideas and research projects and transfer them to such a successful startups.
So I think, the first observation I have is that things in academia there are differences, but also similarities between academia and industry. So one of the similarities that in both cases, what you want to do is like solve particular problems, right? Maybe sometimes, very rarely, problems which haven't solved before, but in most cases, you want to solve existing problems which are kind of important better, right? Um, so, so then, some of the projects in academia inherently are going to solve some of the problems and, solve a bunch of problems. And some of these problems are going to be more relevant for industries than others. And if you are lucky to solve a problem which is relevant for industry and you have a reasonable artifacts like a system to do so, then it's going to get some adoptions because people are going to use it to solve that particular problem, maybe in a better way. And if that system or artifact gets more and more popular, then you are presented with several options. And the options come in the form are you going to, because people, when they when you use these systems and they are serious of betting of the systems to be part of their infrastructure or things like that, the one question they are going to have is like, okay, so what will happen with this system after the students graduate and so forth, right? It's like, can I bet on it? It's going to be still there a few years from now. Who is going to maintain it? Who is going to add new features, evolve it, and so forth? So that's kind of the question. And then you on this, as a people who were involved in the project, started the projects, there are a few options. So one option, it's about, hey, you decide that, okay, it's not worth it, so you are going to drop the project, whatever it happens, it happens. The other option is that maybe you are going to donate the project to another company to continue develop it, or the last one is to start a company, right? So in many of these cases, the projects like to companies, that kind of was a process, right? Started to work on a project. The project was fortunately solving a problem people care about. The system we build or the artifact we build to solve the problem, got traction, was good enough for people to use it, and becomes more and more popular. And now you are confronted with these kind of questions about what to do. And in quite a few of these cases, decision was to start a company, which was a lot of times the decision was driven by the students themselves. I did help with that. So, but that's kind of in short. The one thing I want to make sure and I want to be very clear about all these projects, all these systems, we build or open source, right? We are coming from Berkeley, and as you know, that Berkeley had this long time tradition in developing and pushing open source, all the way from Unix, FreeBSD, right? Unix before Linux, from networking stack for the internet, and like TCP/IP, the first database, relational database ingress, and many more.
So actually, that leads me to my first question, around the nature of continued open source commitments. And I ask this because we do have a decent amount of like investment type folks who watch our podcast, and I've been fascinated by the value that vLLM and SGLang have had as unifying frameworks in allowing any model, any reasonable LLM to run on a wide variety of hardware, right? Like AMD, NVIDIA, etc. And I don't know that much yet about Infract or Radix Arc, but I worry that these companies, have a sort of vested interest in potentially taking away some of the juiciest parts of the next innovations that would otherwise be merged into those projects. And do they try to compete kind of like with Together and Fireworks AI, or how do you see them? And can you can you say for sure that vLLM and SGLang will stay open source?
I think, that's hard. So first of all, this both Inferact and Radix Arc are early on. So there are still a lot of things to figure out about the business. So that's number one. In terms of your question, it's about remaining open source. I do think that they are going, and I do hope they are going to remain open source uh, for the foreseeable future. And I think one of the reasons for that is that it's a competitive market and environment. Um, and so I think that alone, it should encourage the open source uh, motion. And, it's even, it's like vLLM, it's SGLang, it's TensorFlow, NVIDIA's offering as well, TensorRT-LLM. And yeah, so I think it's enough to drive the open source for quite a bit.
So, I want to ask about so your recent like talks frame an AI stack, right? That like you from scaling workloads down to inference with like now vLLM and SGLang, both kind of like maturing. Where do you think is the real remaining bottleneck? Is it memory, communication, scheduling, or maybe something else less obvious?
Yeah, that's a good question. So one thing, yeah, we actually, when we look at some of these problems and when we started some of these projects, one of the things we did consider about the trends to see whether the trends are going to be very important, the relevance of the problems you are going to solve, right? It's like if, say, you focus on solving a particular bottleneck. If that bottleneck disappears because of the trends, then your solution always will be no longer relevant. So I think that's kind of important aspect. So now I think that taking a step back, I think that the biggest challenge I can see is that the sheer complexity of the stack. It's growing, it has grown order of magnitude compared to what was 15, 20 years ago. Just to be very, just to, and again, instead of, I'm describing the problem here, again, I think the problem may require many things. But when we did Spark, it was, started in 2009, so I don't know, like 2010. So it was 16, 17 years ago. When we did that, it was still complex because you are talking about distributed systems. Distributed systems are more complex than single node or single systems, fundamentally because you need to deal with failures, communication, and many other things. But still, if you are talking about the environment, the clusters you're deploying the systems on, we are talking here about Hadoop, Spark. They are homogeneous clusters, so more or less the same nodes, and then and then each node has Intel CPU or maybe AMD. That was the biggest delta back then. And maybe you have hard drives and they are connected by the Ethernet, right? That's kind of what you have. And then so then on top of that, you are going to have this kind of Hadoop and Spark, which are also pretty, so to speak, they're distributed, but they're pretty regular parallelism, right? It's data parallelism, and you have this kind of stages, and each stage consists of tasks, which each task is basically doing the same kind of work for different data partitions. You partition the data, and then you shuffle between the stages. And now fast forward today, and it's so much more complexity at all levels. If you think about the clusters are not only distributed, you have a huge heterogeneity, right? You don't have only CPU, GPUs, but if you look at the GPUs, accelerators, and so forth. So like the last time when I checked, like for vLLM was supporting hundreds of different types of GPUs and accelerators, right? Then it's not only that, it's also the networking. The networking is far more complex. You have RDMAs and InfiniBand and things like that. And then the hierarchy, the topology of the cluster, network topology is very important, right? Because now you are going to have not only kind of server, you connect servers, you can have, rack level servers like NVL and 72. You can have then pods, right? This kind of a lot of racks, which is tightly connected together. And then you look at the applications. The applications are, workloads are so much more complex, right? It's not some kind of regular parallelism. But you have nested parallelism. You have so many things which, because they are driven not only about training or you have post-training and inference. If I look at the inference, how complex it became, right? You have different kind of parallelism, 7 different kind of parallelisms, like data parallelism, tensor parallelism, context parallelism, sequence parallelism, expert parallelism, and so forth. So you have all this complexity, and then things are moving so fast, right? Because every year you have a new model GPUs from every major provider, like look at NVIDIA, right? And these are pretty different. They introduce new instructions as the bottleneck changed. Finally, because you ask about this, it's not the challenge, is not only one particular gap, that people try to optimize the entire stack, right? It's like useful. Usually, when you build a complex system, what do? You divide it in kind of some components, modules, have clear interfaces between them. And this allows you to conquer complexity because now you can worry about developing these components more or less independently as long as you maintain the same interface between them. But now that typically when you do this modularity, it comes with overhead. You pay the overhead, some overhead, right? And people are not willing to pay that overhead because, you train a model, it can cost billions of dollars. So then what before was okay, if few percent you pay for overhead to have this kind of nice modular system, which kind of is more evolvable, it's easier to reason about it. Right now, 1%, if it costs you $1 billion to train is 10 millions, right? So then they break the layering, all these solutions, cross-layer optimization. So it's so much more complexity. So I think that conquering that complexity, I think that's kind of is a key. And even in the case of one workload like inference, that's alone is so complex.
And do you think what will be the direction? Do you think that the algorithms will try to follow the infrastructure and what efficient, like how to design like efficient algorithms for this infrastructure, or the other way around, like we try to go and to build infrastructure for algorithms that we think are promising?
I think one, of course, one answer is going to be like, hopefully, things will stabilize, and then we are going to have more time to think about what are the right abstraction, what are the right components. The other answers, it's about, you need to figure out maybe other ways to develop this kind of software, to develop the stack, right? So that's why you are talking about, and we've been looking at using AI to optimize and even synthesize some of these components in the stack. Hopefully that will be much faster, right? Because if developers cannot keep up with it, with all this kind of complexity and the speed of evolution of the ecosystem, then hopefully AI can help you to, like, that's a promise, right? It improves productivity of the engineer, so you can do things much faster. So maybe you can keep up. So I think these are the two approaches. You need to think at all and evaluate different approaches in order to solve the problem in this case.
And do you think that, there's these AI code generation agent tools now, Claude Code, Codex, Open Code, which I'm sure vLLM is actually powering a lot of models running it. Do you, I've seen a lot of papers that show that some of the hardest code for any code generation tool to write is anything that's asynchronous or distributed, and et cetera, which includes, the fanciest like GPU attention kernel, like flash attention and et cetera. So do you think that this kind of domain of like inference optimization at the level that vLLM and SGLang, and maybe even at what Ray was doing, is this the kind of thing that you anticipate LLMs and code generation tools will continue to struggle with over time, like relative even to humans?
I think obviously, on one hand, they are going to become better and better, right? We know that. On the other hand, in relative terms, I do expect they are going to struggle more than maybe, say, application level code. And there are several reasons for that. One, there are fewer examples. Like, think about how many distributed systems are out there, right? Versus applications like web application or things like that is like a lot of more. The second thing, the code, the logic is much more complex, right? If you talk about the infra, because again, you need to deal with faults, right? To tolerate failures, recover from failures. You have, if you are talking about the data, you talk about consistency, different consistency levels. And the third thing, it's just much harder, takes much harder to test. And because eventually you generate code, you need to evaluate, you need to test it, right? And there are two reasons it's harder to test. One, it's because the sheer space for testing is much larger, right? Because again, you have different dimensions, like I just mentioned a few of them: data consistency, reliability, actually number of nodes as well. You have, and each of these new dimensions, which you do not have necessarily, like for instance, failures. If for the application we are using now, it's not a big complicated to handle it, right? Because it's called this fate sharing. It fails for all of us. And basically we restart it, right? But in distributed systems, this is much more subtle. So again, so this means that the number of cases you need to test for is exponentially bigger. And the other one, it also takes more time, right? You need to set up the system, you need to start the nodes, so all of this takes more time. So I think for that reasons, I do expect in relative terms, this model to struggle more with this infrastructure applications than user-facing applications. But the other thing is about, for any kind of applications, you still need to make sure, and I alluded to this, is about how do you make sure that the generated code is going to align with your intent. It's going to do what it's supposed to do. And I think this is going to be, for a while, one of the biggest challenges, right? Because
And how,
you see, it's like, it's like, in some sense, if you look about how do you create, how do you solve, how do you, when you are talking about a problem, or you're going to talk about an artifact, typically what you have, there are three phases. One, you come up with the idea about what you want to do, or you formulate, or you pick the problem you want to solve, right? Then you come up with the solutions. You write the code, or if it's a math problem, you come with a proof, and then you can, or the idea for the proof, and then you check that your solution really solves the problem, right? And what these models do, they commoditize the middle part, coming up with a solution, generating a solution, right? Generating code. But then you are going to be left still with trying to figure out, and of course you can use LLMs to try to help you to figure out whether the code is correct. But at the end of the day, it's like, I think it's very hard to outsource the entire verification to LLMs, right? Because, if you write a piece of code, it's not the LLM vendor going to be liable if it's a problem. It's you are going to be liable.
so how do you see like the future, like the solution? Because like there are a lot of ideas around like agentic frameworks, right? Like with verifiers for different parts of it, and like, do we need harnesses or not? They can like actually write it by themselves, or like. So how do you see this pipeline? Do you think like we will have the model itself to write its own verifiers, its own harnesses, its own infrastructure? There is, I think, like for example, I think it was Karpati that mentioned it. Like, yeah, maybe we don't need any like external packages anymore, right? The model can write its own packages or like something like that. How do you see it?
Yeah, I think, again, they are going to become better and better, but for some application, here it's a little bit like kicking the can down the road. What I mean by that is that, okay, you are going to have verifiers verifying that the solution which is generated is correct. But how do you know that verifiers are going to handle all the corner cases? Okay, maybe you can have a verifier for that verifier. But you see, it's no longer, and then if you start, it's like actually also, and Andre Karpathy, I think he said, you can outsource your thinking but not understanding, right? So if you don't, you end up with a code which kind of is going to pass your tests, right? And then you are going to deploy it, and then it's going to fail. What you are going to do, right? It's like, oh, I am going to add this as a test and so forth. But it's like you need to have, at least for a while, I don't know what will happen in 1, 2 years, 3 years, but you need to, I think that for the applications infrastructure you care about, you need to understand them, right? No matter how many verifiers you have and so forth. Because the way, here is the way to think about, it's like, at least how I think about. You obviously need to be worried about this reward hacking, right? What reward hacking means is, it means that in our case, it's like the code or the application is not going to behave in all cases like you'd expect, right? And let me, this is maybe too abstract, but let me give you some examples. Like, and sometimes this kind of reward hacks, you cannot even think about them, right? So if you cannot think about them, maybe it's very hard to also figure out, or even for other verifiers to think about it, because the verifiers are also trained on the data produced by humans, mostly. Also now you have a lot of more synthetic data. And we've seen a lot of these reward hacks in our research. Say you want to build load balancers, right? The simplest one. So you get a bunch of requests, and you have a bunch of servers, and you want to redirect the requests to different servers, so that each server is going to be loaded more or less the same. So then you don't have you can serve as many requests as possible, right? So if you serve as many requests as possible, if you can, distribute them evenly across the servers, right? Because if you have a servers which is overloaded, then you are going to hurt the latency and the service for the request you send to that server. Okay, and it's in one case the solution, and one of the metrics here you want to to maximize the number of requests you can handle, right? So, for instance, one solution in one particular case, it was for the solution to maximize the number of requests it can handle by dropping them. Okay.
Mm-hmm.
So now I'm giving these examples because it's one thing you wouldn't think about. Because if I'm asking someone to design a good load balancer to maximize the load it can handle, I wouldn't probably even think about, hey, you shouldn't drop the request, right? Because it's obviously that's the wrong thing to do. And there are many, many, many examples like this. So that's what I'm trying to say, is that how you don't know what you don't know, right? It's like that's kind of the thing.
Do you think that the distributed inference projects that you've worked on, and even going back to things like Spark, do you think that that's still the right paradigm today for most efficient utilization of GPUs? I ask because there's so many different models for how an enterprise can consume them, right? They can directly rent per GPU hour. They can go to per token inference services where they often pay a premium but don't have to worry about idling. And then there's, Spark and cluster-based jobs and scheduling. And I'm just curious what your opinions are on that for any enterprises trying to get their toes into AI.
I think there are at least three things. So one, it's about how you consume this kind of hardware resources. And you can have reservations, you can have on demand and so forth with the reservation is cheaper to reserve this GPU, but if you need to then on demand, but you need to keep them utilized, right? So I think, and then the second thing is about what the framework you are going to use to support the workload on this, hardware, right? And obviously, if you want to handle on demand, then you have a more dynamic framework. If you can acquire logs, acquire new nodes, you can do fundamentally auto scaling, right? But the third thing I want to make sure to say, irrespective, if you think about and you try to oversimplify it, if you want people, if you want to reduce the costs, if you want to even improve your availability, I think the name of the game, you want to maximize the utilization of your most expensive, most scarce resources. In this case of the GPUs, period, right? And if you do that, in order to if you do that, you reduce the cost, right? Because you can do more with less. Also increase availability, right? Because maybe what before I had to do is 10 GPUs, now I use only 4 GPUs. So 6 GPUs I can use for something else. But what this means, you need frameworks and you need systems which can handle heterogeneous hardware, right? Like for instance, if I have things like batch inference, right? You do some data pre-processing, some data post-processing. So, and when you do that, those things you can do on CPUs. So basically in that particular case, I need a framework in which I can auto-scale whatever the number of CPUs so that I feed enough data to the GPUs to saturate them, right? And also to get quickly data out of the GPUs, right? To not waste the resources, the time on GPUs, compute on the GPUs, right? So I think that's one of very important aspects to handle heterogeneous compute. And this is going even more, like even for inference, right? It's like you can have for multimodal, you can have, or even pre-fill disaggregation, you can have different characteristics for kind of GPUs for pre-fill, and then token generation, output generation. You can have even different GPUs, like for instance, if you have video, right? Because you can do decoding and coding can happen on cheaper GPUs, while if you have in the middle some transformer doing inference, um, then you want to deploy it on a much more powerful GPUs. So I think that's kind of the name of the game. At the high level, the name of the game, you want to maximize the utilization of your most powerful resources. And typically means, especially for more complex workloads, that you need to support heterogeneous compute, because this will help you to use cheaper compute, cheaper instances to saturate your most expensive instances.
Do you think so? Like, there is now a huge debate about compute, right? Like, no one had enough compute. Everyone are running to find GPUs. Do you think this is something that will change in the future in terms, like, right, we'll see like more efficient models, or like maybe somehow like find ways to have the same models, but like to train them or like serve them the inference in more efficient way?
Yeah, that's a very hard question.
This is why we are here.
I, yeah, well, I think, I don't think that this will continue at the same level of scarcity, but there can be ups and downs. I think if you remember, actually, toward the end of the last year, it wasn't such a high scarcity. Actually, the price of the GPUs and so forth are going a little bit down. I think what happened, it was in February with the releasing of Opus and Codex, I don't know, like the coding agents and the agentic workloads. Then this dramatically increased the load, right? Increase the amount, and there are also very successful applications. And then everyone is racing to build better models for coding, right? And I think that's kind of this transition, which was very fast, then immediately overnight increase the load in terms of, again, the length of the context you have to train on and things like that, and the model size increase as well, which creates this scarcity over the past several months, which was never like almost like before. But you do expect that eventually this, not continue at the same level. But then maybe you are going to have a new workload, which are going to be another big bump in kind of the load, and then create another kind of scarcity. So I think it's going to be a little bit up and down. I think in terms of models, yeah, I mean, as long as people believe that better models are going to power, like obviously as a scaling law continue at some level, like, and then more data, bigger models and so forth, more compute, is going to lead to better models. You are still going to see that kind of race. It's natural. Of course, for different application domains, you are going to have better, even fine-tuned models or post-trained models are going to do very well and to be much cheaper and so forth. If you are an enterprise and you are going to use your data to fine-tune these models, I think that's also you are going to see quite a bit. But I don't think that the top models are going to just suddenly stop increasing in size or stop, right? And people, they do optimize them, like, as you know, right? It's like, by the way, all this optimization, going back to what I mentioned earlier on, about complexity just lead to much more complexity, right? Because if you look at these models, like what they try, first of all, was this kind of transition to mixture of experts, which are much more complex, obviously, because than dense models. And now you have this so much work on attention, right? It used to be all the layers have the same attention mechanism. Now you have different layers, different attentions. Within the same layer, now you have different attention. Maybe you're going to have, you have this kind of learned attention per token basis. So this complexity is going through the roof again. But people try to do it, right? But it's one of these things, right? Because there is no question the models are becoming more efficient. The system are becoming more efficient, right? For the same model, for the same power, for the same accuracy, the cost of serving, right, per token is going to drop dramatically like a rock, right? But at the same time, people, this is not enough to compensate for the desire of the people. They can take these gains, and the way they take it, I'm going to train even bigger models on even more data, because now I can also generate a lot of data using the harnessing and using all of these agentic loops. Yeah.
But do you see that like a future, let's say near future, that it will end, that the complexity will be too big and will not support this like increase in intelligence?
It's a concern, but I think that what people will focus more and more kind of like specializing the stack for a single model or thing like that. So I think you'll see it, and what would happen, right? But like, for instance, if you think about transformers, everything right now, it's optimized for transformers, right? Software, libraries, everything. Recipe, we know they are optimized for that. Hardware is optimized for that, right? But this hyper optimization, the biggest problem is that it's very hard right now. It's make it harder. It's never impossible right now. Almost nothing is impossible unless you prove mathematically. But it's much harder to come up with new models, new ideas, right? Or you can come up, but to make them successful, right? Because you need to be 100 times better, right? Everything else is kind of, you get this optimization at all levels for the existing technologies. That's what I think it's the concern, right? And you are going to do certain types of attention mechanisms, and then the next generation of hardware are going to optimize for that. So now, even on the paper, you have a better attention mechanism because the hardware is not optimized for that. You may have problems for that one to be successful, right? So that's kind of the things. But I do think this will happen, and it's already happening. You are going to really optimize for different accelerators, for different architectures, on the entire stack.
Do you think that the model inference engines will, well, first of all, do you think that enterprises in general will want to focus more on the very top of the line foundation models, which are often, closed source, OpenAI, Anthropic, or is there going to be a push more towards open source models? And where do you think the trajectory is on them ever catching up or even exceeding closed source?
Look, we don't know, because, but if you are an enterprise, if you are any company at the application level, what do you want is to own as much of the stack. You do not want to be just a wrapper, right? Or even, you need to be very careful about how much of the value you can capture, right? Even Cursor, which was a very successful application, right, on, in the most, successful market for AI application coding, it was very hard to stay independent, right? So, and they try to get out of it, but by training their own model. I think that probably maybe they should have started that 2 years ago or something like that. But I think that what I'm trying to get to is like every company is going to be hard incentivized to own as much of the stack. So given the choice, absolutely they would like to have an open model, train with their data, because now own that kind of stack instead of sending their data to OpenAI and so forth, right? So, because let's take again, let's do this kind of make exercise, like thinking about even Cursor, right? It's like, if you were to start 2 years ago to train your models, then you have the advantage of the data which you use, you are going to be have most users, you are going to have the most data. So hopefully this will give you some advantage, right? If you delay that, you lose the advantage of the data, right? Because the other competitors will have as much data and they'll have more money, right? So now, of course, with that being said, more important than that is for a company enterprise to create an application which is successful, which they can sell, they can, or features, right? Which gets more users using that features or application and so forth. They generate more revenue or maybe reduce the cost. But make no mistake that, and then this can force you, okay, I'm going to use the best models out there. But everyone will think about, okay, I'm starting, a lot of companies, not everyone, are thinking, I'm starting on this OpenAI or Anthropic models, and then eventually I'm going to migrate maybe to some open models, which are fine-tuned on my data. And then I own more of the stack and it's going to be cheaper. I'm not going to spend as much. So that's kind of incentive is always there. The question then are there going to be, good enough open source models to continue to be, to allow you to do that? I hope
And
that
what,
will be.
what do you think? Do you think the gap between open source and closed source will be bigger?
I think right now is probably 6 months or so, something like that.
What do you think in the future?
I think in the future need to figure out, a better way to create these open source models. Because right now, training the next generation of models, frontier models, is more and more expensive. Each generations, from what I understand, is going to be between 2 and 5x more expensive than the current one. So, which makes this will also raise a barrier for the open source models, right? Because you need bigger and bigger pockets. So I think, we have to maybe come up with more creative ways to train such models.
But what do you think is the bottleneck? Is it the data, the compute, like the expertise?
All of the above. I think that it's basically what you need. You need at least 3 things. You need data, you need to compute, and you need people, right? I think data, if you want to train on the public data, only public data, it's a bottleneck, clearly. But otherwise, you spend money and you buy data like everyone else. Then obviously the compute, which is more and more expensive, and then people, right? And then it's an incentive for the company, right? For instance, maybe this is what probably you want to look at. I guess for someone like NVIDIA will have incentives to have very powerful open source models, right? And they have also the money. So that's kind of one natural promoter. And they do have right now Nemotron and so forth, which is pretty good. But I think that's kind of, you need to think, is like that's kind of make it challenging, right? But I do think that, again, it's like if you have enough money and the company is incentivized, you can do it, right? It's clear that, and you can see what is clear is that it's very hard. There is very hard to get significant differentiation between the models over more than a few months, right? Because, everyone's, Anthropic has a great model now and has had for a while, for at least since February. But, at the end of the last year, Gemini was considered a very, very strong model. Of course, before that, it's open. Now people also Codex 5.5 is very good. So Gemini is going to land, right, later this month, the new version of Gemini. You expect to be very good. So the reason I'm saying that I think that if you have money, the expertise is not like secret about how you do it, right? People still move from the lab. You just need, like Meta, right? Meta has tried to do it, so at the end of the day, if you have enough money, you can be in the game.
And what about Mythos? What do you think? Do you think this is a step function or this is something?
Yeah, step function. There are many models. Like Kimi, obviously. Qwen used to be, it's like Minimax are also good models. GLM, very good models also for coding. So you have a bunch of very performant models. The question is that these companies who create these models are going to continue to do so, because some of them, they started to restrict the license, right? Like Minimax and things like that. So we'll see. The point is that my hope is that there are a lot of constituents in the ecosystem, in the economy in the general, which are incentivized to have a good models. Hardware providers, right? It's like NVIDIA's of the world and others, right? They need open source models because they want to understand the architecture of these models. It's like requirements for the next generation of chips, right? Of hardware. Right, enterprises for sure wants open source models, right? For as you mentioned, any kind of AI application vendors would like to do that. They don't want to necessarily to depend only on this open AI and Anthropic and so forth. Different governments in different countries, right? They want that. So I hope that somehow is going possible to assemble this kind of more coalitions to build very good open source models, continue to do that.
And what about regulation? Do you think we should have we should
What?
regulate regulation? We should regulate models and I don't know the use cases.
You should regulate the use cases. I wrote something recently, and I think that you can do a little bit of everything, but the one thing to think, you have to regulate. I am a strong believer. You need to regulate by outcome, not by capabilities, right? We cannot, like humans, right? We don't regulate you because you are smart, how much smart you are, right? We regulate you. It's like the laws and so forth, what you've done, right? It's not what you could do, what you've done, right? And you have to apply something similar to these models because it's very hard to know because the generality, what they can do. How do you know, right? It's like the generality. It's not like, and the capabilities are continuously growing. So it's not like my computer. My computer is pretty clear what it can do or it cannot do, right? With the models, it's much harder. So I think outcomes makes a lot of sense to me, right? Because, it's like if I cannot even anticipate what the model can do, then how I can regulate, right, my capabilities, right? Or, it was this thing, or this kind of executive orders in the past, or even the California's 1047, right? It's like, trying at some points to regulate by capabilities, right? About how many flops to train and so forth. But the main point is that it's like, if you think about, it's like, doesn't make a lot of sense because the use case and how you are going to apply that is going to be so far more important than capability. If the chips and in a bomb, right, or missile, have much lower power than what you have in your iPhone. So that's kind of that's my
And
position.
do you think like it should be like I don't know, self-regulation, something like what Anthropic has done with a method that like they release to some like to a small number of companies?
No, I think that is concentration of power and it's very bad from my perspective.
Yeah,
Think that
I agree.
I think that you should. I think that's one of the things about the open models. Actually, ideally, it's 360 open models. You can inspect and you can audit them, right? And they are open. Everyone can do that, right? You can have, you know, people and researcher and so forth focusing on that, right? And then once you audit.
Okay, so Ian, thank you so much for this great conversation. Thank you so much for joining us. It was really a pleasure.
Yeah.
Thank you so much.
Yeah. Total pleasure.